All right, as we continue lesson 24 on simultaneous equations, we're going to do a real life example here, and we're going to be pulling in some skills and some tools we've been working on in the past. Okay, so just kind of stick with me because it's everything we've been dealing with linear equations. We're going to put it together now. We're just going to be dealing with two. So Jessica and Carl run at constant speeds. Okay, that constant, we've heard that word before. Jessica can run 3 miles in 24 minutes. Carl can run 2 miles in 14 minutes. They're going to have a race. As soon as the race begins, though, Carl trips and he lays on the ground in pain for 2 minutes. Okay? All right, so it says write a linear equation that represents Jessica's constant speed. Make sure to include in your equation the extra time that Jessica was able to run. So let's just set up the equation and then I'll talk to you about how she gets a 2-minute head start basically. Okay, so speed, distance over time, 3 miles in 24 minutes. Now, remember, we always set that equal to y divided by x, right? Distance divided by time. And we're going to do kind of our cross products here to solve. But before we do that, we want to include in the equation the extra time that Jessica was able to run. She was able to run for 2 minutes, okay? 2 extra minutes. So, remember, this is distance, this is miles, this is minutes. So when we're setting these equal to each other, we're not setting this 24 minutes equal to x. We're setting it equal to x plus 2. And the reason I'm putting it at the bottom is because it's the time, right? She was able to run an extra 2 minutes while Carl laid on the ground. Okay? So this is kind of the trick to this. Okay? When we're setting up these equations, we've done this before, but if someone has been able to run for extra time, we have to include that in right here. Okay? So it's not just 3 over 24, okay, equals y over x. It's 3 over 24 equals y over x plus an extra 2 minutes. If you get here, though, because again, Jessica's running for an extra 2 minutes while Carl laid on the ground in pain, now we solve it the exact same way as we've done before. 24 times y equals 3 times x plus 2. Okay? Simplify each side and solve for y, because we always solve for y. So this is going to be 24y equals, using our distributive property, because remember, it's 3 times x plus 2, not 3 times, just 3 times x. So this is 3x plus 3 times 2 is 6. Then I divide both sides by 24, so I'm going to divide everything by 24. 24 divided by 24 is 1y, that's what I wanted, equals 3 divided by 24. If I were to put 3 divided by 24 in a calculator, okay, I could do 0.125. And you can use that, except we're going to graph this. And it's easier to graph when it's in fraction form. So I'm going to hold off putting it into a decimal for right now. Again, we're not going to be like not super concerned with the form that it's in, but we need to be able to graph things. So I'm kind of going back and forth between decimals and fractions. If I look at 3 and 24, if I reduce both of them, if I divide both of them by 3, I get 3 divided by 3 is 1, 24 divided by 3 is 8. So that's 1/8 x plus 6 divided by 24. Well, I can divide top and bottom by 6, and that ends up being 1/4. Okay? Stick with me. Okay? Now, linear equation represents Carl. Well, Carl, my pink back here, he ran 2 miles. He ran 2 miles in 14 minutes. Distance over time, we set that equal to y over x. Now, we don't have to like subtract 2 or do anything like that because we've already accounted for the extra time. You only do it once. Don't do it to both of them, okay? We've already accounted for it. We're done. So now I can just solve this. 14 times y equals 2 times x. Then I divide both sides by 14 because we always solve for y. 2 14th, well, I can divide top and bottom by 2, and that ends up being 1/7 times x. okay? We're not adding anything on here. If we wanted to add something, we could put 0. That's not changing it. Now notice it says write the system of linear equations that represents the situation. This just wants us to write this as a system. We're talking about the same thing here. They're racing against each other. So we do that by just writing the two equations. Y equals 1/8 times x plus 1/4, and y equals 1/7 times x. And then I put the little bracket there. There's my system. Two equations about the same information occurring at the same time. Now we need to graph them, okay? And just a sketch. It's not going to be perfect here. Now, first thing I want you to do is look at the scales. My x-axis here, okay? Remember, that's the minutes. Our independent variable is always the time. And that's just going up by 1. 1, 2, 3, 4. Okay, so our y-axis here, that's going to be miles. Okay, but look at that's going up by 0.2, 0.4, 0.6, 0.8, 0.1. So it's going up by 2/10 every single time. We got to keep that in mind when we go to graph this. Now remember, we could do an input-output table. We could use intercepts. But let me go back to my different colors here. I'm going to represent this one. This was Jessica, I believe. Okay. 1/8 x plus 1/4. Okay, so this 1/4 right here, I know it's like decimals down here, but remember this is really like 0.25, isn't it? Okay, so I am going to plot my y-intercept, and 0.25, okay, so this right here is 0.1, halfway, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. The reason I put that on there, and it's really hard to see that this is 0.3, but I know that 0.25 is going to come between the 0.2 and the 0.3, halfway, right? So I'm going to put that there. Now, from that point, I'm going to rise 1/8, rise over run. And this, I know, can be kind of tricky. We've talked about this in the past, how we're not just going up one block. If I'm at 0.25, I need to go up 1. I need to go up to 1.25. Okay? So that'd be 1.3 and 1.2, 1.3. So right there is 1.25. Right here is 0.25. Okay? See how we went up 1? And now we can go over 8. Now here's the good news. We can just go over 8 because we're just counting by 8s, right? So I'm going to, from here to here, I'm rising 1. I'm going over 1, 2, 3, 4, 5, 6, 7, 8. Okay? Make the dot big. All right. So now I'm going to do the same for, who's the other person here? Carl. Okay? His has, remember, plus 0, so that doesn't do anything. So I'm just going to put my y-intercept here at 0, and I'm going to go up 1. So I'm going to go up to 1, and then over 7. And you know what I forgot to do was draw lines. Okay? So we definitely need to do that. We're on a nice long line through. And again, there's going to be human error in any of this. So just do the best you can with it. Okay. And then I'm going to do Carl's. All right. Use a straight edge. Find something straight to make these lines. Don't just freehand them, okay? All right. So there we go. We have Jessica right here. And we have Carl right here. Okay, so now we get to use the graph to answer the questions. If Jessica and Carl race for 3 miles, who would win? Oh, this kind of seems like a power standard we've done, right? Well, let's find 3 miles. Okay, well, 3 miles is going to be up here off the graph, right? So if you look, though, Carl has taken the lead. Is Jessica all of a sudden going to like cross back over in front of Carl? No. Okay. So I know 3 miles isn't on here, but if we were to keep going, Carl is going to end up winning, even though he took that 2 minute. I don't want to say break. He was hurt. So, oops. So we're going to say Carl. And when it says why, um, his graph is steeper, right? It's going up faster. Okay. Now, at approximately what point would Carl and Jessica be tied? Okay, so if we read our graph here, Jessica takes off. She gets that 2 minute head start, right? So she's in the lead. And then Carl's racing to catch up because his speed is greater, his graph here is steeper. But at some point, they kind of cross. And it's just going to really depend on where your graph is because I can tell by looking at my notes here. My graph before was a little out here more. All right, guys, so I did take a second there and pause just so I could look at my graphs a little bit closer. My graphs were off just a little bit, and it ended up making a difference in our answer. So when I said that earlier that you want to make sure that you use a straight edge and you're really careful, I take it into consideration when we're dealing with just little differences off. So my graph might look a little different now. You probably had it right to begin with. But when I look kind of where they change, it kind of looks like it's happening somewhere in here, right? Okay. I happen to know it is occurring here at the 14. So, oops, that's not what I wanted to do. I'm going to draw these real quick again. Okay. So understand your answer might be off a little bit, and that's okay. Okay. Because I'll look at your graph and say, yep, your graph was just off a little bit, and that's okay. Just make sure you're using a straight edge, okay? So I apologize for that. I should have been more careful in my graphing. Oops. Okay. And so I'm never going to get this perfect, so I need to stop trying. But I will tell you, where your lines intersect, though, that's really important. That's where your solution is. Because remember, we talked in the past, the line represents all the solutions. So where they cross, sorry guys, totally messed things up now, is important. Okay? Anyway, I apologize. Sake of time, we're crossing right here at the 14 with the 2. Okay? So when it says at what point would Jessica and Carl be tied where their lines intersect? Okay? So that occurs at the point 14:2 approximately, because originally mine looked more like 12 point something. Approximately the 14:2. What does that represent? 14 minutes. And that would be 2 miles. Okay. All right. So big thing to remember here is just be careful in your graph. Use a straight edge. Take into account, remember, if someone's getting extra time to run, you got to add that in when you're setting up their equation.